So today I'm going to talk a little bit different from what the presentations that we had yesterday. And so I'm going to talk about the sulfur chemistry and the aerosol-cloud interactions following the SO₂ from a degassing volcano. So the volcano that I'm going to talk about is the Taal volcano that's located in Philippines. And so we have heard a lot about the particle injection into stratosphere, but this study is going to mainly focus on how these particles can change the dynamics in the lower atmosphere or in the boundary layer, basically. So the study is mostly concentrated over a period of February last year, where we had a Asia IQ campaign, the NASA Asia IQ campaign that was held in Philippines to study the urban air quality. But we had a very short interaction with the volcanic plume that really motivated this to make this study and look for the sulfur chemistry happening with this degassing. Brief background on the Taal volcano. It's a volcano located in Philippines, roughly 60 kilometers south of Manila. It had some recent eruptions in 2021 and 22, and then there has been degassing since then. And one more point about this volcano is it's located inside a crater lake. So we are looking at a lot of water vapor coming into the atmosphere from this particular volcanic degassing. So there may be a bit of hygroscopic aerosol growth and a lot of things that may be affecting the sulfur chemistry. Just to briefly explain the ACIQ campaign, that was mostly held over 4 countries. Earlier, last year, during February and March. But for this study, I'm going to concentrate on the Philippines deployment period that was mostly between 5th and 13th February, with 4 flights on 6th, 7th, 11th, and 13th of February. So the motivation of this study came from this, the AOD from geostationary satellite, the GEMS from the Korean satellite, that we had a persistently strong AOD values, I mean, plume that's not coming from the urban region of Manila, but somewhere south of it. And that was pretty persistent for the entire campaign period that we had. So it motivated us to dig deep into what's happening in there. And so the time series of sulfate aerosols from the first 2 flights. So the top one is the first flight we had on 6th. If we look at the scales of these 2 plots, the first one has values ranging from 0 to 5 micrograms per cubic meter. But if we look at the bottom plot, that's the second flight day. So we had 2 spikes of sulfates, huge spikes reaching up to 40 micrograms per cubic meter. And so that really led us to dig more into the modeling aspects of it, of this volcanic plume. So how do we get the information on the volcanic degassing emissions? The Philippines Volcanic Institute, that's the PHIVOLCS, they have a ground-based spectrometer that's located close to the volcano that estimates 24-hour daily SO₂ fluxes and plume height. So this is just an example report. I have highlighted this SO₂ fluxes and plume height. So, and then the time series that shows for the month of February. So, and the 2 dashed lines that have been put on 7th and 11th are basically the 2 days where we had some intercept with volcanic plume using the in-situ aircraft. So the bit of modeling configuration that we use for this study. So we are using the WRF-Chem model with full chemistry and a chemical transport. And we also have a chemical mechanism that's the RACM made VVS, which has aqueous reactions included in it. And so we added the volcanic emissions to the anthropogenic emission files at a plume height, which was estimated using the reports. Just to explain a bit about the sulfur chemistry that is in the WRF-Chem. So the SO₂ productions majorly come from the emissions of anthropogenic and biomass burning. There is some DMS as well, but the SO2 loss is mostly by the oxidation of SO2, which then converts to SO4 and first converts to sulfuric acid and then converts to SO4. The reason for using aqueous chemical mechanism is also then wherever there is a cloud in the grid box, so the aqueous phase chemistry triggers, so the SO2 is not only oxidized by the hydroxy radical, but also ozone chemistry and H2O2. So this shows a comparison of WRF with the DC-8 in-situ observations for the 4 flight days. If we look at the 7th February, the 2 year spikes that we had, the WRF-Chem is also presenting the higher values of SO4, which goes up to 40 micrograms per cubic meter in the first intercept and roughly to 45 in the second one. So this shows that there is a growth in aerosol concentrations to the later part of the day. There were some instances where we had spikes in the observation and model, but these two are basically the ones that were overlapping. So the next analysis that I'll be showing is mostly concentrated on the 7th flight day. Looking at the AOD evolution from the geostationary satellite products, for the 7th flight day, if we see the top panel shows, the left one is the satellite observations and the right one is from WRF-Chem. We see that the AOD, there's a growth of AOD as the day progresses. So the 4 UTC is roughly 12 noon local time. So this enhancement in AOD infers that there is particle growth and by condensation towards the later part of the day, and there's definitely new particle formation. The WRF-Chem model also has similar signatures where the AOD enhances towards the later part of the day. It signifies particle growth by condensation. Then some comparisons of, remember we had this very small interaction with the plume. So this is the first intercept of the plume, and if we look at the time scale, it's roughly about 3 to 4 minutes that we had a strong sample size of SO2 and SO4. So the top panel showing the SO4 from AMS instruments, and the black ones are the WRF. So the WRF is a little bit over-predicted, but it still captures the high values. It's over-predicted by roughly 50%. And same with SO2 as well. The model overestimates a bit, but if we look at the SO2 to SO4 ratios, it's pretty much aligned with the model, and observations are pretty much aligned. Same thing if we look at the second intercept of the plume. There's a little bit noise in the ratios, but still the pattern is quite well captured in the model. So this signifies the model is doing a good job in capturing the sulfur chemistry and converting the SO2 to SO4, because we are just manipulating or changing the SO2 values, but nothing with the SO4. But the model is tending to capture the process, the sulfur chemistry, quite well. So this is the aerosol composition that we have for the first intercept. The left panel is the DC-8, the right one with addition of the SO2. Then the third panel, that's where we don't have the volcanic emission. It's obvious that there is no such signature of this plume. So if we look at the aerosol composition, it's mostly dominated by sulfate aerosols and a little bit of organics. The sulfate aerosols in WRF-Chem with addition of the volcanic emission does show a peak that is more or less close at the level where we also see in the observations. But one interesting thing was the model is underestimated the organics, the organic aerosols, and one reason for this could be the epochs that may be resulting from the oxidation of isoprene. which we don't have in the model. And the overestimation in the SO4 may be attributed to the SO2 overestimation stats. In the rightmost panel, the red box is showing the SO2 values, and this may be coming from the uncertainties of the initial conditions that we use from the reports. Similar story for the second intercept, later part of the day, where we see much more vertical mixing of the aerosols in the observations. So in the first intercept, we see that there's a maximum peak roughly at 1 kilometers, 900 meters level. But on the second one, it's much more mixed to the vertical levels, which is also persistent in the model. So the metrology and the chemistry in the model may be doing a good job in representing it on shorter time scales. Then we looked at some mass and number distribution in that particular times, that's roughly 5 minutes. So if we look at the number distribution, we see a lot of nucleating particles. If you look at the blue bars in the first panel, in the top panel, so there are a lot of particles in the lower bins. That's the diameter is roughly at 4 nanometer, 8 nanometer, 15 nanometer. So this signifies that there is a lot of new particle formation that's originating from this conversion of SO2 to SO4. And the number of particles, the number concentration per cc is also as high as 10,000 numbers, 10,000, 12,000. The second intercept also has less values if we look at the number concentrations, but that may be because the SMPS had a 2-minute scanning window, and maybe that could be a reason that since we are intercepting the plume for a very short time, the SMPS might have missed it. But yeah, the major thing is, and if you look at the mass distribution, the model tends to increase, the observations, there is more mass in the hair bins towards the later part of the day. So this shows that there is growth by condensation towards the later part of the day. And similarly, if you look at the model highly underestimates the number concentrations. There is similar signature of the model being able to increase the particle mass and number towards in the second intercept, but if you look at the numbers, it's highly underestimated. So one thing for this underestimation of number concentrations might be that the chemical mechanism that we are using doesn't have a good representation of new particle formation, and it mostly condenses on the existing ones. This is just a movie showing the SO4 total column SO4 and the cloud fraction. The cloud fraction is in the red contours, and if we look at the SO4, so we see a clear formation of SO4 then dying out. So it shows a very strong diurnal cycle, and also the plume is sometimes mixed over the ocean, whereas sometimes it's transported long range to downwind towards Malaysia. And particularly if you look at the two snapshots that I took on 9th and 11th, we see a cloud forming over the plume. So I tried to concentrate on the top one, the 9th, that we see presence of sulfate and clouds at the same time. So yeah, we looked at the number concentration differences between when we have the volcanic simulation, volcanic emission and without it, but we don't see a significant change in number concentrations either in the nucleation mode or in the accumulation mode. So then we looked at the mass, what might be happening, that is it only that the number is not changing, or is it the mass? So on the left panel, if we the left panel shows with the volcanic emission and the right one without. And the top one is the Aitken mode, that's roughly at particle size below 100 nanometers, and the bottom one is accumulation mode. So we see that a lot of mass is present when we have the volcanic emissions. If you look at the scales of it, it's roughly like 3 times more mass. So one thing we could conclude that the model is not representing new particle formation, but it's mostly condensing on existing mass, where there is a 3-fold increase in mass right along the track of the plume. So so we took this box that I have drawn, and then tried to compare it with the changes in number, and we don't see a significant difference, even if there is a cloud present over that region, and the number concentrations don't change that much. So the summary of my study would be that adding SO₂ emissions from the volcano simulates the transport of SO₂ and the formation of sulfate aerosols, but the number concentrations don't increase significantly, whereas there is a much more condensation and increase in mass distribution. So for the next step, since the chemical mechanism that we are using may not be having a new particle formation parameterization, we are testing a new chemical mechanism that's a SAPRAC 99 with a mosaic aerosol scheme. So we are kind of transitioning from a modal approach to a sectional approach. So yeah, we tested with 8 bins initially, but now we had a help from PNNL guys. So they have shared a 20-bin mosaic aerosol scheme that explicitly have new particle formation, and the bin sizes start from 0 nanometers. So we had some results recently, like 2 days back. I was looking at it, and I see a lot of nucleation and new particles in the lower bins, and hopefully we'll be having a good comparison with the in-situ observations, where we have comparable number and size distribution, and then we'll go forward to look at the radiation changes and the impact of this increase in number of sulfate aerosols to in like marine cloud brightening experiments, and so hopefully we'll get some good results that can support this impact of sulfate aerosols on the radiation changes in the domain. Thank you.